Welcome back, everyone, for another deep dive.
Mm,
Today, we're going to be looking at this review paper, and it's all about disentangled representation learning in remote sensing.
very cool.
Now, I know you guys out there listening are pretty familiar with machine learning and all the math that goes into it, so
Yeah,
I
yeah.
think you're really going to like this one.
Yeah, this is a really interesting area, and disentangled representation learning really has a lot of potential for remote sensing, so I'm excited to dig into this.
Yeah, for sure. So one thing that really jumped out at me at the beginning of this paper was that there isn't like a single agreed upon definition for disentangled representation.
Yeah,
It's kind of funny how, like, this is such a core concept,
right.
but people are still kind of figuring out exactly what it means.
Yeah, absolutely. And the paper actually talks about two different ways to define it. One way uses this math framework of symmetry transformation subspaces.
Okay.
Gets into some group theory there. The other way focuses on how sensitive individual representation units are to specific generating factors. But even with these slightly different perspectives, the main goal is still the same,
Yeah.
learn a representation that's compact, that's interpretable, and where each variable, lines up with a specific factor that's generating the data.
So it's not just about, like, separating the factors, but also about figuring out, like, what role each one of them plays in creating the data we see.
Yeah.
Kind of like when you're doing a controlled experiment, and you want to isolate a variable to see what effect it has.
That's a really good analogy. And the paper dives into this idea of a causal mechanism behind this whole thing.
Okay.
It basically says that, high-dimensional data, like a remote sensing image, comes from a set of hidden factors.
Uh-huh.
These factors are kind of like the building blocks for the data we observe.
So how does that generation process actually happen according to the paper? I mean,
Okay, it's like a two-step thing.
Yeah.
First, you have this latent representation vector that's randomly sampled from some distribution. Think of it like picking a point in a simpler, low-dimensional space. Then, based on this vector and some conditional distribution, you get the actual data, like the image itself.
So it's kind of like we're working backward from a complicated image to figure out those basic building blocks.
Exactly.
Like trying to figure out the recipe for a cake just by looking at it.
Yeah, that's a good way to put it. And to guide this whole reverse engineering process, there are three key properties that disentangled representations should have, ideally.
Okay, let's hear 'em.
They are modularity, compactness, and explicitness.
All right, so modularity, that seems pretty straightforward, making sure that each latent variable corresponds to, at most, one generative factor.
Right, so each dimension in the representation is dedicated to a single factor. You could think of it like a set of independent knobs, each one controlling a specific aspect of the data.
Okay, so like you could adjust the tree height without affecting the tree density in your representation.
Exactly. Then there's compactness. This is about making sure the representation is efficient, no noise or redundancy.
So it's like compressing a file without losing any important information.
Right. Compactness ensures that the information about each factor is stored efficiently in the latent space. This makes things less complex and easier to interpret.
Gotcha. And then we have explicitness, which basically means we can go back to the original factors.
Yes, explicitness means that the model should be able to decode the latent representation and recover all the information about the original factors. It's like having a blueprint that lets you reconstruct the original design from a simplified model.
Okay, so to sum it up, modularity keeps things organized, compactness keeps things efficient, and explicitness makes sure we don't lose any crucial information along the way.
Exactly.
But how do people actually achieve this disentanglement in practice?
Well, that's where things get really interesting. The paper goes into four main categories of methods for disentangled representation learning: dimension-wise, semantics-based, hierarchical, and nonlinear ICA.
Ooh, now we're talking. This is where things get really exciting. Let's dive into these different methods and see how they approach this disentanglement puzzle.
Absolutely. Let's start with dimension-wise disentanglement, which is probably the most straightforward approach. So dimension-wise disentanglement, it's based on a pretty simple idea. Each dimension of the latent vector directly maps to a single generating factor. Like, imagine a latent space where each axis represents a specific factor, like tree height or, species type.
So it's like a one-to-one mapping between the dimensions and the factors.
Yeah.
But wouldn't that have trouble with like real-world data where things are usually more interconnected?
Yeah, you're absolutely right. Dimension-wise disentanglement kind of assumes that the factors are independent, which isn't always true in remote sensing. Things can get pretty complex.
Right.
And that's why researchers have been looking into other methods like semantics-based disentanglement.
Okay, so how is semantics-based disentanglement different?
Well, it acknowledges that factors often have relationships. They're not totally isolated. So instead of trying to separate everything completely, it groups dependent factors together based on their meaning.
So instead of forcing total independence, we're allowing some structure and connections within the representation.
Exactly. For example, instead of having separate dimensions for object type and lighting conditions, you might group those together in a cluster of dimensions because they're related.
Makes sense.
Yeah.
That seems like a more nuanced approach, recognizing that sometimes you can't or shouldn't completely isolate every factor.
Right. And then there are situations where factors have like a hierarchy. Some factors influence others at different levels.
Right.
That's where hierarchical disentanglement comes in. It organizes the latent variables in a hierarchy to reflect these multi-level dependencies.
So instead of treating all factors as equally independent or dependent, we're building a structure that mirrors the real-world relationships.
Exactly. Think about a forest. You have like forest health as a high-level factor that influences things like tree density and species distribution, and those in turn affect individual tree characteristics.
Yeah.
Hierarchical disentanglement lets you capture these cascading relationships across different levels.
That seems perfect for remote sensing because you have all these layers of information from broad landscape features down to individual objects.
Yeah, exactly. And then the paper also talks about this fourth category, nonlinear ICA. Have you heard of that?
I have, but I'm not super familiar with it.
Well, it stands for Nonlinear Independent Component Analysis, and it's probably the most mathematically rigorous approach of the bunch.
Okay.
It uses a nonlinear reversible transformation to separate independent factors that are all mixed up in the observed data.
Sounds like it's trying to untangle a really complicated knot. How well does it actually work?
It's definitely promising, especially for simulated data where the generating factors are well defined. But when it comes to complex real-world data like remote sensing images, it's still early days. Those images have a lot of noise and complexity, which can be challenging for this method.
So we have all these different methods from the simple dimension-wise approach to the more sophisticated nonlinear ICA. And each one has its own trade-offs between simplicity, flexibility, and how well it works in theory. But how do we actually go from these ideas to training a model that can learn these disentangled representations?
That's where loss functions come into play. These are mathematical expressions that guide the training process. They encourage the model to learn representations that have the properties we want.
So they're like the invisible hand that shapes how the model learns.
Yeah, that's a great way to put it. And the paper talks about three main types of loss functions: modular constraints, explicit constraints, and multi-purpose constraints. Each one focuses on a different aspect of disentanglement.
This idea of using loss functions to guide the training seems really crucial for getting meaningful disentanglement. Let's break down these different types of constraints and see how they work.
Sure. Let's start with modular constraints. These are all about enforcing modularity, pushing the model to learn representations where each latent variable is as independent as possible.
So making sure each dimension or knob
Yeah.
in our representation is really controlling just one thing.
Exactly. One common example is cross-reconstruction loss. This is often used when you have pairs of data that share some common information but also have some differences. Like, imagine two images of the same forest but taken under different lighting conditions.
So we want to separate the forest structure from the lighting effects.
Right. Cross-reconstruction loss takes advantage of this kind of situation. It swaps the shared parts of the representations and then tries to reconstruct the original data. This forces the model to learn representations that cleanly separate the shared information from the unique information.
So by making the model reconstruct the images with mixed up parts, we're teaching it to recognize the independent factors.
Exactly. Another popular modular constraint is mutual information minimization. Mutual information tells you how much knowing one variable tells you about another. So by minimizing the mutual information between latent variables, we encourage them to be statistically independent.
So if knowing the tree height doesn't tell you anything about the tree density, then those factors are disentangled in the representation.
Precisely. And then there's triplet loss. This one is often used when you have semantic labels associated with your data, like knowing whether an image is mostly urban or vegetation.
So we're using existing knowledge about the data to help with the disentanglement.
Right. Triplet loss uses sets of 3 data points: an anchor, a positive sample that's similar to the anchor, and a negative sample that's dissimilar. The loss function then tries to make the representations of similar samples closer together in the latent space while pushing dissimilar samples further apart.
It's like teaching the model to recognize family resemblances between data points based on their labels.
Yeah, that's a good analogy. Now let's move on to explicit constraints. These are all about making sure that the learned representation can be decoded to get back all the original factors.
So we haven't lost any pieces of the puzzle during the disentanglement process.
Exactly. A simple example is self-reconstruction loss. This just measures the difference between the original data and the data reconstructed from the latent representation. The smaller the difference, the better the model has captured the essential information.
So it's like checking if you can rebuild the original structure from the blueprint you've created.
Precisely. Then there's mutual information maximization. This might seem counterintuitive because earlier we were talking about minimizing mutual information.
So now we want a strong connection between the latent representation and the original data.
Right. The goal here is to make sure the latent code captures as much information as possible about the data so we don't lose anything important during the encoding and decoding.
It's like making sure the blueprint has all the details needed to perfectly reproduce the original design.
Exactly. And similar to cross-reconstruction loss, there's latent similarity loss. This is often used when you have data pairs that share some invariant information, even though they vary in other ways, like two images of the same forest taken at different times of year.
Okay, so the foliage might be different, but the underlying structure of the forest is the same.
Right. Latent similarity loss encourages the model to encode this shared information consistently across different instances. This helps to disentangle it from the factors that are causing the variations.
That seems really useful for remote sensing, because often we're interested in how things change over time.
Absolutely. And finally, there's cross-entropy loss. This is a familiar concept from classification tasks, but in the context of disentangled representation learning, it can be used as an auxiliary task to help the latent codes represent specific factor information.
So it's like adding a side quest to the main training objective, making sure the model learns to represent certain aspects of the data effectively.
Precisely. For example, you could train a classifier to predict land cover types based only on the latent code. This would encourage the latent code to accurately encode land cover information, which helps with the overall disentanglement goal.
Like making sure the blueprint not only represents the overall structure, but also has specific annotations for key features.
Exactly. Now let's move on to the final category, multi-purpose constraints. These are designed to promote multiple disentangled properties at the same time using a single loss term.
So it's like multitasking during the training process.
Exactly. One example is cycle consistency loss. This is often used in image translation or style transfer tasks. Imagine you want to disentangle an image into its content and style components.
So separating the what from the how of the image.
Right. Cycle consistency loss involves a two-stage process. First, you disentangle an image into its content and style. Then you swap these components between two different images and try to reconstruct the originals.
So you're mixing and matching content and style from different images,
Yeah.
and then challenging the model to reverse the process.
Exactly. And this process forces the model to learn representations that are both modular, cleanly separating content from style, and explicit, enabling accurate reconstruction of the images.
Like shuffling a deck of cards and then challenging someone to put it back in the original order. A clever way to enforce both separation and reconstruction fidelity. What other multi-purpose constraints are there?
Another interesting one is latent regression loss. This is used to encourage the latent code to represent specific generative factors. Well, imagine you have a latent code that represents tree height.
Okay, so one dimension in our latent space is dedicated to tree height.
Right. Latent regression loss would involve training a separate regression model to predict the actual tree height based on this latent code. By minimizing the error of this regression model, we encourage the latent code to represent tree height accurately and efficiently.
So it's like embedding a mini-test within the training process to make sure the latent code actually carries meaningful information about the factor we're interested in.
Exactly. And finally, there's the evidence lower bound, or ELBO. This is a key concept in variational autoencoders, which are a popular class of generative models used for disentangled representation learning.
Variational autoencoders are pretty powerful.
Yeah.
How does ELBO contribute to disentanglement?
ELBO is a bit more math-heavy, but basically it encourages the latent codes to capture a complete representation of the generative factors while also promoting independence between those codes.
So it's finding a balance between completeness and separation.
Right, and that's the strength of multi-purpose constraints. They can tackle multiple aspects of disentanglement at the same time, which makes the learning process more efficient.
This overview of loss functions has been really helpful. It's amazing how these mathematical tools can be used to shape how the model learns and guide it toward disentangled representations. But how do we know if our models are actually doing a good job? How do we measure their effectiveness?
That's where evaluation metrics come in, and that's exactly what we'll cover in the last part of our deep dive.
Welcome back to our deep dive on disentangled representation learning for remote sensing. We've talked about the main ideas behind DRL, gone through different methods, and even explored those intricate loss functions that guide the training process.
Yeah, it's been quite a journey.
But now the big question is, how do we know if these DRL models are actually working? How can we be sure they've really learned to disentangle those complex generating factors?
That's where evaluation metrics come in. These metrics give us a way to measure how good those disentangled representations are. They provide a quantifiable framework so we can really assess if the model has successfully separated those underlying factors.
So like judges in a competition scoring the models based on certain criteria.
Exactly. And just like we have a whole toolbox of loss functions, we also have a variety of evaluation metrics. Each one focuses on a specific aspect of disentanglement. The paper categorizes these metrics into three main groups, which align with the core properties of disentangled representations we've discussed: modularity, compactness, and explicitness.
That makes sense. Having a structured approach to evaluation seems really important for understanding a model's strengths and weaknesses. Let's start with modularity metrics. How do they actually measure the separation of factors in the learned representation?
A popular metric is the beta VE score, which gets its name from the beta VE, a type of variational autoencoder often used for disentangled representation learning. This metric uses the idea of controlled factor variation.
I remember the beta VE has this parameter beta that controls the trade-off between reconstruction accuracy and disentanglement. But how does the beta VE score actually measure modularity?
Imagine you have a data set of images with factors like object shape, color, and rotation. The beta VE score works by fixing one factor at a time, let's say shape, and then changing the other factors randomly. This creates pairs of images that differ only in those varied factors.
So we're essentially setting up controlled experiments within the data itself, isolating the effect of a single factor by keeping it constant while the others change freely.
Exactly. Then the model encodes these image pairs into their latent representations. If the representation is truly modular, the latent codes for the two images should be very similar in the dimension that represents shape and different in the other dimensions.
Right, because shape is the only factor that's held constant across the two images.
The beta VE score then uses a classifier to try to predict which factor was held fixed based on the differences in the latent codes. If the classifier is accurate, it means the model has done a good job of isolating that factor, which indicates good modularity.
So a high beta V score means the factors are well separated in the representation. Are there other metrics that use a similar approach for evaluating modularity?
Yes, there's the factor VAE score. It works in a similar way to the beta VE score, but it uses a slightly different method to generate data pairs and predict the fixed factor.
So another variation on the controlled factor variation theme.
Right. Then there's the modularity score, which directly measures the statistical dependence between each dimension of the latent code and each generative factor. It uses mutual information for this.
Mutual information keeps popping up. It seems like a key concept in disentanglement assessment.
It is. A high modularity score means that each dimension of the latent code is mainly informative about one and only one generative factor, which suggests good separation of factors.
So minimizing dependence between latent variables is a big part of modularity assessment. But modularity is just one aspect. What about compactness? How do we know if the model is representing information efficiently without unnecessary redundancy?
One common compactness metric is the mutual information gap, or MIG.
More mutual information. I'm getting the hang of this now.
Great. The MIG is similar to the modularity score in that it uses mutual information to quantify the relationship between latent code dimensions and factors. But instead of looking at the overall strength of the relationship, MIG focuses on the difference between the two highest mutual information values for each factor.
So, for example, if we have a factor like tree height, we look at the two dimensions in the latent code that are most informative about tree height and see how much their mutual information values differ.
Exactly. A large difference means that one dimension is carrying most of the information about that factor while the other one isn't contributing as much.
And that suggests good compactness, because the information is concentrated in a small number of dimensions, reducing redundancy.
Exactly. Another metric is the separated attribute predictability, or SAP score. This one uses a regressor or classifier to predict the true value of each factor based on each individual dimension of the latent code.
So if we have a dimension for tree height, we'd train a separate model to predict the actual tree height using just that dimension.
Right. A high SAP score means that individual dimensions are effective at predicting specific factors, which suggests a compact and efficient representation.
Okay, so we've covered modularity and compactness, ensuring separation and efficiency in our representations. But what about explicitness? How do we measure the model's ability to recover the original factors from the latent representation?
The paper mentions the explicitness score, which directly assesses how well the model can decode the latent representation and accurately reconstruct the original factor information.
It's like checking if you can completely reverse engineer the blueprint from the simplified model, making sure no important details were lost.
Exactly. A high explicitness score means the model can successfully reconstruct the original generative factors from the latent representation, which shows good explicitness.
So far, we've talked about metrics that evaluate individual aspects of disentanglement. Are there any metrics that take a more holistic approach looking at multiple properties together?
Yes, there are. One example is the disentanglement compactness and informativeness, or DCI score. This comprehensive metric evaluates all three key properties at once.
So the DCI score gives us a more complete picture of the model's performance instead of just focusing on individual strengths or weaknesses.
Right. The DCI score uses a combination of techniques like regression analysis, entropy calculation, and prediction error analysis to assess disentanglement compactness and informativeness all together.
This overview of evaluation metrics has been really insightful. It's fascinating to see how researchers have come up with so many different ways to measure and analyze the performance of DRL models. It really shows how important rigorous evaluation is for driving progress in this field.
Absolutely. The choice of which metric to use depends on the specific task, the data you're working with, and your research goals. There's no one-size-fits-all solution, and often researchers use a combination of metrics to get a well-rounded understanding of how the model is performing.
This whole exploration of disentangled representation learning has been incredibly enlightening. We started with the basic concepts, then delved into the details of training and evaluation. It's given us a much deeper understanding of the challenges and the potential of this rapidly evolving field.
Definitely. To recap what we've learned,
Yeah, let's summarize.
disentangled representation learning aims to uncover and separate the hidden factors that generate complex data. It offers a lot of advantages in terms of interpretability, controllability, and robustness. And there are various methods to achieve disentanglement, each with its own strengths and weaknesses. So choosing the right method depends on the specific task at hand.
Right? And the training process is guided by these loss functions that shape how the model learns and encourage it to create disentangled representations. Then we have these rigorous evaluation metrics that give us quantifiable insights into how well the models are performing. And these insights help guide future research and development. Disentangled representation learning feels like this amazing tool that could revolutionize how we understand and interact with complex data, from remote sensing imagery to medical records and beyond.
Absolutely. I'm really excited about the potential of this field. The ability to untangle the complexities of data holds so much promise for scientific discovery, technological advancement, and just a deeper understanding of our world.
Well said. Thank you for joining us on this deep dive. We've only scratched the surface of this fascinating field, but hopefully it's sparked your curiosity and given you a solid foundation to explore further on your own. Until next time.